Hello everyone, I am Rayat Imtiaz Hossain. I'm going to present this paper titled Framework-Agnostic Semantically-Aware Global Reasoning for Segmentation. This is a joint work with my supervisors, Professor Leonid, Sigal, and James J. Little at University of British Columbia. And the work is supported by NSERC, CIFAR, Government of Ontario, and Vector Institute. Our work is motivated by the simple fact that we humans use global context for effective visual reasoning. For example, if we look at this blue patch over here, we are not sure what it represents. It could be a stone path or it could be simply a blue colored brick. As we see more context to this patch, we realize that this patch actually belongs to the roof of this house. Adding more context, we see that this is not a simple house, but rather it's a dock because there is a boat parked inside and it's surrounded by water. Therefore, as we see, as we have a better understanding of the global context, we get better at visual reasoning. Therefore, global context is essential for pixel level tasks like segmentation. The limitations of the existing approaches to global reasoning are that they are either based on patch-wise interactions like these VIT and swing transformer, or they involve interacting between tokens which are aggregated in a manner which does not have any strong semantic notion, like as we can see here. So the goal of this work is to design a component which we call SGR that aggregates features into latent tokens in an object-centric manner, such that features belonging to a particular instance of an object, like here a particular instance of a car, gets aggregated into a token. And we want to do this without using any additional instance annotation. And once we obtain the semantically meaningful latent representations, we want to globally reason between them so that we end up getting better contextualized features, which we hypothesize would help us in achieving better segmentation accuracy. So the contributions of this work are that we proposed a component which we call SGR that aggregates image features into latent tokens in an object-centric manner without the need of additional instance annotation. This aggregation process is weakly supervised using connected components of the ground truth segmentation mask, which acts as a lower bound for the number of instances. And importantly, this SGR component can be plugged into a wide variety of backbones and segmentation frameworks, both convolutional and transformer-based backbones, and also per pixel classification or mask classification approaches of segmentation. And when we have observed that when we add our component on a variety of different segmentation frameworks, we end up having better segmentation performance. Additionally, we design losses that encouraged the latent tokens that we have to be distinct and disjoint from one another. Furthermore, we also proposed a couple of metrics to quantify the semanticness and diversity of the tokens that we get. So here is an overview of our proposed model. An XY position embedding is added to image features to obtain position-aware image features. We then perform a dot product between these position-aware image features and a set of learned concept embeddings to obtain concept-aware projection matrices, which we also call concept regions. These concept regions are weakly supervised using ground truth connected component masks, which we will discuss in the next slide. These concept regions project image features into latent tokens in an object-centric manner, such that only features from a particular concept or an object are aggregated into a token. These semantically meaningful tokens are then passed to a transformer encoder to perform a global reasoning between them. Once we obtain a globally reasoned and better contextualized latent space, we then back-project them into image features before passing them onto the segmentation head for the task of segmentation. In this slide, we will discuss how we greedily match a set of concept regions to given ground truth connected components. So in step 1, we perform Hungarian matching for one-to-one assignment between the best matching concept regions with the ground truth connected components. In the next step, out of the remaining connected concept regions, we greedily select k top concept regions that minimize the given cost matrix and assign them greedily. Once matched, if two or more concept regions gets matched to a particular connected component, like the circle in this case, we define losses such that a union of these concept regions encompasses the entire connected component, and that we have added additional constraint to ensure that these concept regions are distinct and disjoint. In this slide, we show the quantitative results obtained by adding our component with existing semantic segmentation frameworks. As you can see, regardless of the backbone or type of segmentation approach you use, when we add our SGR component on top of these frameworks, we get a consistent improvement in performance across all the three datasets. Our results are underlined with these red lines. In this slide, we see a visualization of our tokens. Compared to the latent representations of GCNet and mask former, we can observe that our tokens are much more semantically meaningful and diverse, and are able to disambiguate between different instances of the same object. For example, in the first image, we can see the first token is able to disambiguate the left cow from the right. In the second image, the rightmost horse, and in the third image, it can distinguish different instances of the car. However, compared to that, the tokens of GCNet and mask former are not able to disambiguate different instances, and they are less semantically meaningful and diverse. And just to remind you guys, we did not use any additional instance annotation, but rather we use connected components as a lower bound for the number of instances and use it as a form of weak supervision. Here, we look at the metrics that we defined to quantify the semanticness of tokens at both class and instance level. The first metric, which we call semanticness, measures the mean entropy of the histograms of the concept regions of tokens at both class and instance level. The lower the entropy, the more semantic the token is at class or instance level. Now, we need a separate measure for class and instance level, because as we can see in the second token, it is very good at pulling features from cars, but poor at pulling features from an individual instance of a car. Now, this metric semanticness can be minimized if all the tokens always pull features from the same components or object. However, we want our tokens to be diverse and extract features from different instances or different concepts. Therefore, we proposed a second metric, which we call diversity, which measures the standard deviation between different token histograms. Here, we show the quantitative measure of the semanticness using the metrics we proposed. As you can see, whenever we added SGR component on top of the existing segmentation framework, we obtain tokens which are more semantically meaningful and diverse at both class and instance level. Here, we look at some of the qualitative results on COCO dataset. As we can see, adding our SGR component to two different segmentation framework improves the overall segmentation quality. To summarize, we proposed a framework-agnostic component called SGR that aggregates visual features in an object-centric manner and globally reason between them. This component can be plugged into a wide variety of segmentation frameworks to achieve an improved performance across three different benchmark datasets. Second, we proposed metrics to quantify the semanticness of the latent representations. Thank you for your patience and listening to my presentation.